Save that video.
No, finally, I mean to this one. So that is
Okay. Start.
Nobody knows.
Sorry?
Nobody knows if it's working.
Yeah. We cannot know. Okay, so last 3 lessons. I still have to sit for Friday, so because some of you asked me to move in the afternoon, would be okay for everyone to do it in the afternoon, 2 o'clock or 4 o'clock?
that's okay.
Okay, no problem?
No.
Okay, so let me know, just maybe today I will talk with Patrizia and I have to finalize something in my office. Okay, so last 3 lessons. 3 lessons taking account the second part of the course, let's say, which relates with the stratification. Okay, so stratification is quite complex. That's why we will address it only in actually 1/3 of the course, not half of the course. Because what is really important in GFD, as you have seen, is the presence of rotation. So with rotation you can really change the perspective of usual classical fluid dynamics and start to describe large-scale motions. But it's important also to have an idea of what is the effect of the stratification. So we will talk specifically of what we call static stability. Okay, so we will quite usually, quite often use the terms stability and instability. And in particular, what we can think, and we already considered in the first lesson, is that if we have, so in this moment, we basically change from a perspective which is on the plane, on the horizontal plane, so 2 dimension, to something which is on the vertical, okay? So before, we almost didn't consider the vertical, okay? Because if you remember, Taylor-Prudman theorem, do you remember what that is saying? Taylor-Prudman theorem? How much is dz of is 0, okay? So, actually, we never considered any shear, okay? This is shear, so it means that we have things like this. The only shear that we considered was that related to what? Which was the only shear, I mean the only difference in...
Due to contact with the boundary.
Yeah, Ekman, yeah. With stress, Ekman, okay, boundary. Okay, so only in presence of a boundary we have something like where this theorem do not apply, because this theorem is valid only in the geostrophy. So when we are upside, okay, from the boundary layer. Do you remember the Prandtl theory? We have an interior which is geostrophic, very good, very ideal, and then we have a boundary layer. Okay, now, apart from this very special case, we want to relax this this hypothesis and start to consider variation in the vertical. In particular, the variation related to the stratification. Because up to now, another big hypothesis, very strong hypothesis that we did was to consider a homogeneous fluid. Okay, so you remember that this is always the famous prime. Okay, so this is the variation that scales as delta rho. Okay, so far delta rho was equal to 0. Now we start to have a delta rho which is no longer equal to 0. Okay, so have a look to that system in the slide. So what they say is consider a fluid in static equilibrium. Lack of motion can occur only in the absence of horizontal forces and thus in the presence of horizontal homogeneity. Okay? So we are moving from something which was, in some sense, vertically homogeneous to something which is horizontally homogeneous. We are moving to something which was rigid in the vertical, because you remember that the extreme case for rotation was the Taylor column. Okay, so the Taylor column was something which is constantly moving, following the isobath, and which is let's say the perfect inhabitant, we say, of this geostrophic world, ideal geostrophic world. Now we are moving on something which is no longer vertical, rigid, but horizontally rigid. In particular, if we have this case here, which is very, very common, we have it is differently colored. So we have light fluid here and heavy fluid here. Okay, so this is a stable condition. As soon as I don't take a parcel from here and I put here, and what I can understand, what I can imagine is that this parcel will come back here because it will feel itself heavier than the surrounding, okay, because this parcel is here due to the fact that we have a incompressible fluid. So it means that the volume will not change. And so if I move the parcel up, I expect that the parcel will feel itself heavier without, with respect to the surrounding, and will come back. The same thing, if I take the parcel here and I put here, what do you expect is that the parcel will go up. Okay, so if we try to mathematically describe, because this is intuition and it's good, it's correct, it's something that we can consider, but so let's consider that position, that layout there, and try to explain the second law of motion, okay? Force equal to mass multiplied by acceleration, okay? So in this case, we expect that there will be an acceleration because we are taking our parcel, we are moving so there is an external action, okay? We are moving the parcel up so that we will leave the parcel from a state of rest, so velocity equal to 0, and the parcel will go down, so there will be a velocity, and so the parcel will be accelerated. So we can express that our Newton law is equal. So this is the mass of the parcel, density multiplied by volume. This is the acceleration. And what is the force which is applied to this parcel? It's nothing more than the buoyancy or gravity or Archimedes. Do you remember Archimedes buoyancy force? Archimedes pull. So which is GV, and then we have so we have the fluid weight minus the parcel weight. Okay. So of course, according to the sign of this difference, we will have a pull, an upward pull or a downward pull. Okay, so don't forget that we are still in GFD and we are still working with the Boussinesq approximation. So Boussinesq approximation, we know that is rho equal rho 0 plus rho prime, okay? So this rho prime is the same that we initially, up to now considered equal to 0. So we can do this thing and say that rho 0 is much larger than rho prime, always, you remember, always except when it's multiplied by gravity. So we must be very careful here, but we can be very absolutely relaxed to substitute rho z here with rho 0. We can let v, so we have this expression. So actually, this is my delta rho. Okay? So this is the scale of the density variation. So I can express the value in z plus h as the value in z plus 0 over dz h, which means that I'm using again a Taylor expansion because I can say that this is very small, okay? So this is very small. Also h we can consider very small. So we can make an expansion in the neighborhood of our position z. So if we have this expression here, we can use this expression and substitute the difference with actually the gradient of our density field. So we will have G rho dz h. So from this I can put everything on the left hand side. And what I obtain is a equation, differential equation, second order in H. This means that I can solve H in function of t. Okay, so I can obtain the variation in time of the quote of the distance with respect to the reference position, which is z. Okay, so now we will define a new terms, which I will call it n squared. So if I look to this term here, this is dimensionally speaking. This is so rho and rho can be neglected. So I have acceleration divided by a length, okay? So this is 1 over second square, okay? So 1 over second square means that this is a frequency squared, okay? So I can define a new term which is called Brunt-Väisälä frequency, from the name of two scientists. Väisälä was from Finland and Brunt was British, which is equal to minus G rho d rho dz. So this is, of course, since this is positive because it's a squared dimension, this is of course defined when d rho dz is negative. What does it mean that the rho dz is negative? It means that if I am in this situation there, this is z and this is rho. Okay, so it means that I'm going to have heavier fluid in the bottom and light fluid on the top. Okay, so which is stable condition according to our intuition. Okay, so if we consider this expression here, we can solve our system. We can use H double dots. You know that when you use double dots, it means the second derivative in time, plus m squared H equal to 0. So the solution of this, any mathematician, brave mathematician, very easy, come on.
Omega. We went omega frequency?
Omega, yes, we have, well, we have n frequency. Okay, so yes, we have a frequency, so what is the solution is?
Exponential.
Is an exponential, is an imaginary exponential. So we will have that H, don't look at the PDF. H is equal, you are, I'm joking. So this is the solution, okay? Which means that I will have, in the real part, H0 cosine of n over t. That's why, of course, n becomes a frequency which is actually the square root of this term here. Well, very interesting. So it means that our intuition actually was correct. But even with more analysis from the mathematical point of view, what we can understand is that, okay, so I take this parcel, I put this parcel up, this parcel feels itself heavier than the surrounding, so go down. But when it goes down, it takes acceleration. So all the energy, the potential energy, it is transformed in kinetic energy. So it overpassed the equilibrium point and go down as soon as all the energy is released. When it arrives here and the velocity becomes 0, it feels itself buoyant with respect to the surrounding, and so it go up. And so, in absence of any damping effect, because of course, if I put some damp here, this will be like some e to the minus something in time. So there will be a sort of how to say it, damping, yes, of the effect. But in absence of this, so in the most easy case, we have this solution here. Okay? So this is when we have stability. In the opposite case, when we have d rho over dz positive, we can define a new, we can rewrite our equation like this, when we will have that minus d squared will be equal to minus g rho 0, d rho over dz, and this, of course, this is positive, so this is negative, so I can put, and which means that d squared is positive. So, in this case, I have a real exponential in time. Okay, so the solution is a sort of explosive increasing. Why? Because if you revert the layout of our system, so we have lighter fluid here and heavier fluid here, if I do the same, and if I put my parcel up, the parcel will still be buoyant with respect to the surrounding, because the surrounding are going to increase the stratification. This means that from a first position, it will still be buoyant, it will continue, and so on. Okay? So, if the first case was, let's say, initiated by an external intervention, so we are there and we put something, the parcel up, or there is, for example, a flow which for some reason perturb this equilibrium status and move the parcel up and down, giving the effect of the oscillation. In this part, to maintain the inverse stratification, we need to have a source of energy, okay? Because this situation here is naturally unstable, okay? So it means that, for example, we could, so if we have strong density, heavier fluid here and lighter fluid here, for example, we should have like a heat source on the bottom or a cold source on the top. Okay. For example, this is the typical situation that gives rise to thunderstorm. Okay. When we have thunderstorm, we have in summer, very typical, we have very hot air here, and if we have a cold flow coming from the mountains, for example, this creates convection, and convection is practically the effect of the instability, okay? Because this can be, this effect is not just for one parcel, but can be for all the parcel, okay? So all the parcel of my fluid column are transferred to the top. Of course, to conserve mass, I will have other parcels that will come down, okay? That's why what we have, of course, this model is a little bit too simple to explain this, but I will have some convection cells, okay? And so what I obtain is that I will have hot, warm air that goes up and then condense and then create, then I will have interaction of masses of different characteristics, different thermodynamic characteristics, so I will have thunder and blah blah blah, and then rain and so on. Okay? And this is a very, I mean, thunderstorm, if you remember, are not affected by rotation. Okay? So we can consider this without taking in consideration any rotational effect. Okay, so we discovered our nice Brun-Weiser frequency. The other step that we want to do is to find a sort of analogy, because analogy always helps in also for study, I would say. So in describe the natural phenomena, so we can try to find an analogy with the rotation. So with the rotation, you remember that we had an animational number, which was the Rossby number, which actually was the ratio between the advection term and the Coriolis term. Okay, so the stronger is the Coriolis term, the smaller will be this Rossby number. In the maximum case, in the extreme case, when Rossby number is much smaller than 1, we will have the geostrophic flow and blah blah blah. So with the F-plane, we will have also the horizontal divergence, Taylor columns, and so on. Okay, so let's have a look to the Rossby number. Rossby number actually is a ratio between a velocity scale, a frequency scale, and a length scale. Okay, so the question is, do we have analogous of Rossby number for the stratification? This is something that can be helpful. Okay, so this is, as I said before, we will restrict to stably stratified flow. Okay, so for the moment, we consider that kind of flow. And this is an example. So this is a typical situation that you can find in the atmosphere or in the ocean, where you have, you don't have any kind of effect related to rotation, but you have an obstacle which has a scale L, can be like, for example, mountain ridge. We have a velocity flow, current flow, wind or current, which has a scale U. And this flow is stably stratified, so we have the scale of stratification, which is m squared, over h. You remember that when we introduced the scale of motion, h was always related to the scale of delta rho. Okay, so h is always related to the scale of density variation. Okay, so density variation is actually defined by the gradient, the vertical gradient of the density field, and so is represented by n squared. And the obstacle has a vertical scale, delta z. So, do you remember what happened for the geostrophic flow in this case? If we have a flow coming from here, a geostrophic flow, what could yes, go out, or if we consider this as like the top view, we can only travel around the isobar. Okay, so we cannot never overcome this for the geostrophic flow. But for the barotropic flow, what will happen?
We conserve the column.
Yeah, we conserve the column, so we conserve not the column but the potential vorticity. So we will have a change of vorticity here and another change of vorticity here. Okay? Okay, so let's look what happened to in this case. So we can try to analyze again the scales of this problem. So the time scale for a flow to transverse our obstacle is L over U. Okay, so I'm a parcel. I'm driving. I'm flowing with velocity U. The obstacle has length L, so it will take to me a time L over U. I can also represent the vertical distance delta z, which is the scale of my obstacle, but will also be the scale of possible vertical movement. Okay, because think about a parcel which is here. Okay, so as you can see, there is a sort of gray shading. Okay, so here it means that the density is higher than here. So if I have to go up, it means that I have to use the velocity in order to overcome the obstacle and to move from, let's say, heavier fluid to lighter fluid. Okay, so I'm going, in some sense, this is the same action that I did before, like taking the parcel and putting the parcel up. So in some sense, I'm flowing against the stratification. Okay, because the stratification, in some sense, will report my position to the initial one. Okay, because of the Brunn-Weiser frequency. Okay, so the oscillation. So if I am going up, there will be something, a force, a restoring force that will bring me down again, and so on. Okay, so delta z, which is actually can be defined as the scale of vertical velocity multiplied by t, because I suspect that there will be a sort of, if I'm moving here, so I will have a component in this direction and a component in the other direction. So this can be also written like W L over U. Okay, so one step plus that we can do is that if we consider delta z over h which means how much is the ratio between the vertical displacement and the total displacement. So it will mean, okay, how much the parcel will be raised up with respect to the total height. So this is nothing more than this over h, but this can be also written like w over h over u over l. Okay? So this ratio here scales. Okay, now I put equal, but we are always considering scaling analysis. So this means that I am this term here scales like the ratio between the vertical convergence and the horizontal, the vertical divergence and the horizontal convergence, or the vertical divergence and the horizontal convergence. Okay? Which was something that we already thought at the beginning. You remember that we analyzed this when we considered the first approximation of the GFD, and you remember that we understood that the vertical convergence can be maximum equal with respect to UL, okay, in the most general case. Okay, so now we can also consider our delta rho, so the variation of density. So delta rho will scale like the gradient multiplied by delta z, and this gradient here we can use the expression of n squared, so that we can relate delta rho directly to n squared. So if we consider delta rho over dz, we can use this expression, and we will have which is equal to rho 0 n squared g w n over u. Okay, so one step again, the pressure. So now we are considering the only effect of the pressure will be the hydrostatic pressure. We are in the vertical, so this will be G H delta rho. This is the scale of my pressure, hydrostatic pressure. So I can use this expression and write GH rho 0 n squared over G WL over U. Which means that we can even remove the gravitational acceleration. Okay, last step is to find a scale for the velocity, because up to now we do not, we have the velocity u as a parameter, but we can relate with the analysis of the horizontal balance, the pressure to the velocity. So in the horizontal balance, not considering the rotation, we will have something in steady condition, which will be like u dx plus v, u dx. So advection which will be like on okay. So if I do not consider friction, I do not consider the variation, local variation in time, and I do not consider the rotation, this is the balance in the horizontal. So how does it scale? It scales like u squared over L and P rho 0 L. So from this we can find a scale for P, which is rho 0 u squared. So from this, we can find that u squared scales like p over rho 0, which scales like n squared WL over U H. Okay? So this is P, H, rho 0 n squared WL over U, divided by rho 0, I just obtained H n squared WL over U. So from this, I can multiply and divide by H, and what I take on the left hand side is the term so I have u squared n squared h squared, which scales like w over h u over n. Okay? So u squared divided by n squared and h squared, and what remain on the right hand side is w over h over u over n. So this term here tells us that if u is smaller than n multiplied by h, it means that the w over h will be smaller than u over n. Okay? So the smaller is u over nh, so the slower the parcel is traveling, or the larger is n over h over u, which means the stronger is the stratification. It means that the vertical displacement will be smaller than the horizontal one, which means that at the extreme, when this will be very, very strong with respect to this will be very, very small with respect to this. So we can define a new, this is a dimensional number, okay, because we have everything which is a dimension. We can define a new adimensional number, which is the Froude number, again from the name of a scientist. So Froude number is exactly u over n h. And actually, the smaller, when the Froude number is very small to respect to 1, it means that the vertical divergence or convergence will be very small with respect to the horizontal one. And since our vertical displacement scales exactly like this, the ratio between the vertical divergence convergence and the horizontal convergence divergence, it means that delta z will be much smaller with respect to h. So in the extreme case, which is similar to the Taylor column, when we will have the Froude number, that now, don't forget that it is a velocity scale divided by a frequency and a dimension and a length scale, which is analogous to the Rossby number, okay, velocity, frequency, and length. So in the extreme case when the Froude number will be very, very small to 1, very small with respect to 1 going towards 0, what we will have will be that which means that the stratification will be very, very strong. It means that the parcel will not be able to increase its vertical displacement and will be constrained to overcome the obstacle. In the case when the obstacle is, let's say, symmetric along the y, because don't forget that we are going to have y direction also here. So the the parcel will be constrained to remain on this side. Okay? So this extreme effect is called blocking. Also horizontal blocking. Okay? So in the case of horizontal blocking, which is quite common, for example, when in the atmosphere we have a mountain ridge and we have a strong stratification on one of the two sides, we will have that the flow will be constrained to remain there. There will be no mixing. And this is extremely important. So I'm using this word mixing maybe for the first time. So it means that there won't be any kind of recirculation of the air or the water, but with the air is maybe more intuitive. And which means that we as humans that live here, we will breathe always the same air. Okay? So this is a very special situation that can occur, for example, in valleys. And if the valleys are polluted, like for example in Italy, where you have okay, this is more or less Italy. Trieste is here. Okay, this is Venice. This is the Po River, okay, flowing. And this is the Po Valley. Pianura Padana in Italiano. Okay, Po Valley is actually constrained among two mountain ridges, the Alps and the Apennines. Okay, what happened? Quite common in winter is that here we have a very strong stratification. Okay, and this stratification actually can also become even more, even stronger and stronger, so that it is not possible to overcome the stratification, so to mix the air. Which means that since the area is very strongly industrialized, people working and living and breathing air in the Po Valley actually are breathing very polluted air. Okay? So a situation like this actually, which is described by a variation of density, like here, can be even more exacerbated by the fact that if we consider this like the temperature, so that is not, you know that we can create a strong relationship between density and temperature. No? So if we have high density, we have also cold temperature. Okay, so temperature actually is like this. Okay, so high density means low temperature, and low density means high temperature. So this situation here actually occurs when we have this layer of air which has a temperature which is actually on the ground lower than at, for example, let's say 50 meters, because or 100 meters. So on a scale h, which is about 100 meters, we have the temperature not decrease as we should expect. Okay, because we should expect that if we go up in the mountains, temperature will be colder than in the at the surface level, at the sea level. But the situation that we have seen here create a profile of the vertical that actually is reversed, and what happened is that after that the layer of higher stratification is over, we will have that the temperature will start to decrease. Okay. So this happens, for example, when we have fog. In case of fog, there is no possibility because the ground is very cold. So light, the energy from the sun cannot reach the ground. So we have a decreasing temperature in this layer, and we have practically the establishment of a very strong situation, strong stratified situation. If we go up about 100 meters or even 200 or whatever, we will see, and we look at the downward, we will see like a sort of sea of fog, sea of cloud, and we will see the sun, and actually the temperature will be even larger, even higher. This is a situation that can happen here in Trieste when we have, maybe last days, not today because today we have Bora, but yesterday and the day before, we had some sort, it was not fog, it was like mist, okay? But if you go up in the mountain, not 100 but 1,000 meters, you can find very beautiful day with a very nice sun. But if we have like fog like this in Trieste, which can happen when you have the advection of fog coming from the Po plain, actually from the Po valley, which is moved slowly against over the northern Adriatic and reach Trieste. But Trieste is like Trieste is here, and then we have hills, okay? And this scales about 250 meters, okay? So if we have fog here in Trieste, and we are here, and if we go uphill in Opicina, for example, okay, or Prosecco, so about 250 meters, and you are here, actually you can feel warmer temperature. You can look at the fog, and you don't see the city, and you can see the sun. So this is the effect of strong stratification and thermal inversion, which is related to strong stratification. Okay, so again we used a very simple mathematical consideration, extremely simple, just a sort of scale analysis to explain something which actually happened in reality. Okay, so this is the scale of vertical divergence convergence over horizontal convergence divergence in case of stratification. If we come back for a minute to the scale, to the rotation flow, what we will have is that our, if you remember, we have the continuity equation, okay? So this scale like U over L and this scale like W over H. So actually Rossby is a scale which measures the importance of the vertical divergence or convergence with respect to the horizontal one. Okay? So when Rossby is very, very small with respect to 1, so we are going towards a geostrophic flow, this means that this is very, very small with respect to this one. That's why we can neglect this in the very extreme case and consider only the ideal case of non-divergence on the horizontal. But of course, this is a sort of approximation, okay? It's the ideal situation. In the most general case, we can allow that our vertical divergence or convergence scales with rho 0. So it means that for the totally rotating flow, the ratio between vertical divergence and convergence and horizontal convergence divergence is rho 0. So we have this for the rotation, and we can rewrite here fruit number square for the stratification. So now, since most of the flows happen occurs when we have both cases, both rotation and stratification. I want to now make the same analysis by considering a combined effect of rotation and stratification. So, what is how can I express this fundamental ratio, which is, don't forget, the scale of delta z with respect to h, in the case of rotation and stratification. So if I have rotation, of course, I also have a scale in the horizontal, which is given by the balance between the Coriolis term and the pressure gradient. Okay. Of course, if I am in the stratified flow, I don't care about the rotation. Okay, so we can use the expression of W, which is here, and we put W here. So from here, I have the W is related to pressure, so it will be pressure multiplied by U over rho 0 H n squared L. Then I have L over H, and then I can express U, because now I have the scale for U, which is P omega rho 0 L. No, sorry. Because it's at the denominator, right? Because it's here, okay? So P omega rho 0 L. And then I multiply again and divide by U. So I can recognize U squared over n squared and h squared, U squared over n squared h squared, which is the fruit number. I can avoid P, and then I have rho 0 as well, and then I have L as well, and then I have U multiplied by omega L over U. So this is fruit number squared, and this is 1 over rho 0. Okay? So what we have is fruit number squared over rho 0. So we can write here so this is the case of stratification plus rotation, this is the case only for rotation, and this is the case only for stratification. Okay? This is how the fundamental ratio between, which explain many things, because explain how the motions actually are distributed in the horizontal and in the vertical. Okay? Can scale like Rossby number in the rotating flow, like fruit number in the stratified flow, and like fruit square over Rossby in the combined case. So again, if you say that if these two numbers are much smaller than 1, of course we have that the vertical divergence or convergence is much smaller than the horizontal one. And the extreme case will be the Taylor column here, when we do not have any kind of no motion in the vertical, and the blocking here, okay? So, we obtain this situation, but something that we have never to forget is that this term here is always constrained by having the vertical divergence and convergence always smaller than, or at least equal than the horizontal one, if we are again far from boundaries. Okay. So this means that the foot number will be smaller than rho zero. So in any case, even if we have both effect, we will consider fruit number square smaller than Rossby. So what means is that u square, n square, h square will be smaller or maximum equal to u over omega n. From this, we can obtain that L will be limited to a value which is n square, h square, omega over u. And so if we have a specific velocity u in a specific stratified flow characterized by n over a specific height which scales at h, and in a system which rotates with omega, our flows will be constrained by having a horizontal scale which is maximum equal to this value. Or on the other side, the velocity will be limited to n square, h square, omega n. And of course also we can find a limit for h by keeping L and U as parameters. So this helps us to consider a situation which in some sense takes everything, I mean both stratification and rotation, as equally important. And we can define a new adimensional number, which is the Burger, I think this will be German, like hamburger, which is defined as nh over omega n square. So, practically, the ratio between Rossby and fruit number. So the Burger number is practically a ratio between two velocities. Okay, so a velocity which is given by the frequency related to the stratification in the vertical scale, and the frequency given by the rotation multiplied by the horizontal scale. Okay, so is another, let's say, another view of the ratio between the vertical divergence convergence and horizontal convergence or divergence. So now we can consider typical GFD flows where you remember that H is much smaller than L, but also omega is much smaller than n. So omega is 1 over 24 hours, okay? N is usually 1 over a few minutes, something like that. Okay? So the frequency of oscillation is much larger, of course, than the frequency of rotation. So we are considering two different systems, we say the same system, which is rotating very slowly with respect to how much is oscillating in the vertical. Okay? So if you consider this, you can understand that if h is much smaller than L and omega is much smaller than n, we can have actually that Burger number can be order of 1. Okay? Because if this term is much smaller than this, and this is much smaller than this, we can have that, contrary. This is much smaller than this, and this is much smaller than this, we can have that the numerator and the denominator can, there is a possibility that they have the same order of magnitude, so we can have Burger number order of 1. So we can put everything, all our consideration in a graph which has Rossby number, the value of Rossby number on the x-axis, the value of the Froude number on the vertical axis. So this is as the caption says, the recapitulation of the various scaling of the ratio of vertical convergence divergent WH to return the divergent convergence UL as a function of the Rossby and the Froude number. So if we are very close to this point here, we are considering very small value of Rossby number. Okay, so these are, if we consider this as Rossby equal to 1 and this as Froude equal to 1. Okay, so it's a sort of discrimination when rotation starts to be important and when stratification starts to be important, which was, if you remember, the question that we made in the very first lesson. Okay, where are the effects, which are the effects, or when we can consider that stratification and rotation are important in our flows. So here, flow is influenced mostly by rotation, with respect to here, where flow is influenced mostly by stratification. So in this case, we know that Rossby is the one which scales with the ratio between horizontal divergence and convergence. So it means that when Rossby is much smaller than 1, actually this term here must, the ratio of Froude square over 0 must be much larger than Rossby. So it means that we are, between this and this, but this is much stronger than this. Okay, so we have that. That means that Froude square will be much larger or much larger than Rossby. But it is Rossby which governs the scaling of the vertical divergent convergence with respect to the horizontal one. Of course, in the other case, we have that when Froude number is very small, so we are in this area here, we will have the contrary. So here, Froude number will be much smaller or much smaller than the Rossby number. And finally, we have the situation, the mixed situation, where we have that Froude number is order of Rossby number, and the flow is influenced by both rotation and stratification. If we have this one, it means that if we look at Burger number, actually the Burger number is equal to 1, or scale like 1. And what we obtain here is the scale related to flows which are affected by both rotation and stratification. And if we consider, again, values like this, so 1 over 24 hours, 1 over 10 minutes, and L, which for the ocean, H, which for the ocean is, for example, 1,000 meters. So now I'm considering, for example, only the surface layer of the ocean, okay? So not the entire depth of the ocean, but only the surface layer. The one which is characterized by a stratification, which is typical because, like in the atmosphere and in the ocean, you can have that the surface layer, the layers which are in contact with the air will be warmer than the layer which will be deeper because of the energy penetration, of course. Okay. For the atmosphere, I can consider 1 kilometer. So 1 kilometer is not 10 kilometers of the troposphere, as we said at the beginning, but just the first layer that we also call the atmospheric boundary layer, okay, which in some sense is not stratified, but is constantly mixed. But okay, let's keep this as a value. So, making again the calculation, we will obtain 50 kilometers here and 500 kilometers here. Okay? So again, we are obtaining a sort of natural scale that, if you remember, we extracted at the very beginning when we just considered not all the Rossby fruit and blah blah blah, but the two, let's say, intuitive dimensional number which related the rotational effect and the stratificational effect over the fluid. And actually, this is nothing more than the mesoscale again. Okay? So, this is very interesting because if you make a Fourier analysis of atmospheric flows, you will see that there will be a peak in the energy at this at the wave number corresponding to this wavelength. Okay, so it means the same in the ocean. So mesoscale again is the scale which contains most of the energy of our geophysical fluid dynamic flows. Okay, good. So now we can make one more step and consider something a little bit more complex. So, complexifying again our topic. So now we are considering a system which actually is a little bit simpler than the other one, because in the other case we had a vertical density which was dependent on z. So let's say like linearly changing in depth. Now here we are considering a two-layer stratified fluid where we start from an initial situation where we have a layer which is actually heavier, so we have that ρ2 is larger than ρ1. So these two are homogeneous, okay? It's like if we are, for example, in the case before, we are just considering like, okay, like two layers where here we have ρ2 and here we have ρ1, okay? Like discretizing the linear change in depth or in height of our density field. So, but no longer, we also give a velocity in the bottom side of our system and in the top side of the system with u2, which is actually smaller than u1, for example. And we will have that h1 and h2 actually will be equal, for example, to half height, okay? So where would you like to put the center of gravity of this system? According to this line, down, up, in the middle? Down. Okay, we can say that the center of gravity is here because, of course, this is heavier than the other one. Okay, let's now think that we have complete mixed. So now we are having the shear. Now we are having shear because velocity here is different from velocity here, is going to transfer energy in order to completely mix the system. So we will obtain a system which has homogeneous velocity along the entire depth and homogeneous density. Where is the center of gravity here?
The middle.
In the middle. That's great. Very old-fashioned animation. Okay, so if the center of gravity has been raised from here to here, what does it mean? We have, yes, we have, this is the second, you're right, but yes, we have an increase of the potential energy. And which is the cause of the potential energy, of the increase of the potential energy?
I think
Sorry? Say again. Say again, don't worry.
The mixing.
The mixing, yes, the mixing. So it's the kinetic energy, which actually has reduced, okay? So we had a kinetic energy here. Of course, the sum of potential and kinetic energy is conserved because this is an isolated system, but we are transferring the kinetic energy related to the velocity shear to the potential energy in order to raise the center of gravity of the system. So we can actually calculate these two terms because it's quite easy to do. So we will, since this system is, okay, if I take a specific volume, this will be like certain delta z multiplied by the surface, okay? So I can consider different layers which sum up will this will be dV, so it means that if I integrate all the volume, I will have practically the total volume, okay? Which means integrating S over dz. But since S, I can consider it constant, I can simply add S multiplied by H, okay? So I can take into account and calculate the delta U, or potential energy gain. Because as I said, my center of gravity has been raised, so it has been a gain of the potential energy. So the potential energy gain is actually the potential energy in the final state minus potential energy in the initial state. And I expect that this will be positive, okay? Because I know that my hypothesis is that this is larger than this one. So the potential energy at the final step will be the integral. This is, let's say, potential energy divided by S, okay? So you will find it by analysis of the dimension. So I integrate over G Z dz. So this is the potential energy in the final situation, where I can simply write rho here, which is the value of the density, the homogeneous density in the final step, minus I will have in the initial condition, so I will have rho 2 in the first part, so in H2, from 0 to H half, rho 2 gz dz plus from H2 to H rho 1 gz dz. Okay? So, how much is rho? Can we calculate rho? How much is the value of rho? What do you think? So if we consider, sorry? Is, no, yeah, this is, can be ocean or atmosphere. And don't forget that this is always the density perturbation, okay, the value. So, what we can say? We can say that the mass must be conserved. So we must say that the mass at the final must be equal to the mass of the initial state. So mass of the final will be density rho multiplied by the volume, and this will be rho1 plus rho2 multiplied by the volume. So more specifically, I can write SH, so rho SH, which is equal to rho1 SH half plus rho2 SH half. Okay? So in this specific situation, I have that rho is simply rho1 plus rho2 over 2, which is the average. Okay? So there is no other particular reason why we have a density which is different from the average. There is, geometrically speaking and thermodynamically speaking, the only possibility that we have is that one. So if we substitute here rho1 and rho2, and oh, sorry, this is wait, because maybe I was incorrect. So this is the density, not the density perturbation. Okay, so thank you for this. Because now, when we are considering all this, yeah, it should be, because this must be the energy. So if we make all the calculation that you can do as homework, what we will obtain is 1 over 8 rho2 minus rho1 g h squared. It's very easy, okay? So this is really very easy. So now, yes, this is the difference of density. So this scales like delta rho, okay? So this is our rho prime, okay? And we cannot say that rho2 is order of rho1, because we must say that rho1, rho2, which for our hypothesis is larger, will be equal to rho1 plus a certain delta rho. Okay? So this is the density variation. And actually, since rho2 is larger than rho1, I have the potential energy gain, of course, is a gain, so it's positive. Okay, so of course we cannot. We always have the Boussinesq approximation behind, so we cannot neglect this. Even this is a delta rho, so it would be like rho prime actually. We cannot avoid because it's multiplied by g. Okay, so this is the reason why we are having a potential energy gain. So we can do something similar for the kinetic energy. So delta K will be the kinetic energy loss, which will be in the opposite kinetic energy at the initial state minus kinetic energy in the final state. You can calculate also on the other case, it's not important. So how we express this? Again, in the initial case, we will have, we integrate, and we use now rho 0 u initial square dz minus integral rho 0 u final square dz. Okay, so rho u square is actually the scale for the kinetic energy in every vertical layer. Okay, so I simply use the rho 0, where in this case I can say that rho 0 is order of the 1, is order of the 2, because here I could have, of course, used the rho 1 and rho 2, so split this in 2 like I did here, but actually, since I'm just multiplying by a velocity squared, Boussinesq say, okay, you can neglect the variation in density, so I can use a reference density, ρ0, which is a background. So it's like I have ρ1 is ρ0 plus, let's say, ρ1 prime, and ρ2 is ρ0 plus ρ2 prime. Okay? And actually, when I did the difference of this one, I obtained the difference of the prime. Okay? So, if we make the integration also from here, where we just have, with similar consideration, that the final velocity will be equal to the average of the initial velocity because of the momentum conservation, okay? So, exactly like the mass, but this is applied with the momentum. Mass multiplied by velocity, exactly the same. Of course, this is a very fortunate case because of the geometry that we are having, okay? But something that still is useful. Okay, at the end, what we have is 1, 8, 0, u1, u2, square h, which again is positive. Of course, it's a loss. I mean, it's the value of the loss. So it means that the kinetic energy at the beginning is actually larger than the kinetic energy at the final state. Wow, very interesting. So what we obtained now is something that can help us to define that we have complete mixing as in that example, when the loss of kinetic energy will be larger than the gain of potential energy. So it means as much as I mean the velocity shear is in some sense supplied to the system, it means that I'm keeping to release kinetic energy, so I'm keeping to transfer energy from the velocity shear to the stratification, and so I'm sustaining the mixing. Okay, so I'm keeping the center of gravity rising up. Of course, if here there is like a sort of switch on, switch off of the velocity shear, the flow will come back like the initial state. So if I completely switch off the velocity shear, the equilibrium state will come back to a situation where we will have heavier fluid on the bottom, lighter fluid on the top. That's why I can maintain this complete mixing when this kinetic energy loss will overcome the potential energy. Which means that I can make again a ratio between the two terms, and I have ρ2 minus ρ1 gh over, so I just take the ratio between the potential energy gain and the kinetic energy loss, so it's this divided by, so 1/8 can be neglected, and so I obtain ρ0 u squared. Of course, this can also be read like delta rho gh over ρ0 delta u squared. Okay? So delta u is the scale, okay, don't make confusion, but delta u is the scale of my shear, delta rho is the scale of the stratification. So shear actually is the one that is going to sustain the complete mixing. If the shear is enough, I can support the mixing. If the stratification is stronger than the shear, of course, the mixing cannot happen. in this case, I can have a localized mixing. So when this term here is larger than 1. So in this case here, the mixing does not occur completely over the system, but just in a very small area, very small layer close to the interface. So we can restrict our analysis to this situation. So when we call about localized mixing, we will see that a two-layer shear flow is always unstable. So what does it mean? It means that, again, if we have a situation like this, ρ2, ρ1, a vertical shear, in this case, it's a little bit more complex, say, one in one situation and one in another situation. So this is the evolution in time of the situation. So we will have a flow which is in this direction and another flow which is in another direction. Okay, so if we are considering like two semi-infinite planes. Okay, so over the only position where there is shear is just at the interface. So in time, what will be observed is that I have a sort of creation of systems like this. Okay, actually, this is the mechanism which explains the surface waves of the ocean, where you have air and ocean. And this is called Kelvin-Helmholtz instability. Okay? So Kelvin-Helmholtz instability will start with an initial perturbation of wave number k, and we will see that the system is always unstable to short waves, so two waves short enough, I would say. And as waves overturn, the vertical and lateral dimensions are comparable. Okay, so this typical pattern, this vortex that you can have in the vertical plane, will have horizontal dimension comparable with the vertical dimension. So let me see if there should be okay, this is a very nice experiment which shows you.
This experiment to look at the Kelvin-Helmholtz instability of a shear layer between two layers of fluid begins with a clear layer of fresh water on top of a denser red-dyed layer of salty water
Rho1,
in a long horizontal tank. To set up this experiment, the empty tank is tilted and then half filled with fresh water. Very slowly, so as not to mix the fluids, dyed salty water is introduced from the bottom corner of
very
the
slowly.
tank.
Okay, this is a sort of the setup of the
This has been
experiment,
speeded
which of
up
course
slowly.
is interesting because you don't have to mix the fluid before when you want to mix actually. Okay?
Still working very slowly, the tank is tilted back towards the horizontal, and frequent checks are made that the fluids are not sloshing around. When all is ready, The tank is tilted quickly to an angle of about
So
8 degrees.
before slowly and
The
then
dense, salty water
sharp,
flows downhill,
sharp.
while the lighter, fresh water
shock.
flows uphill, and thus shear is generated between the two
Now we
layers.
have shear.
Suddenly, the interface between them becomes unstable.
Beautiful, huh?
Let's watch that again closer up. Remember, the lower dyed layer is flowing to the left, while the clear layer flows to the right. The instability initially forms a distinctive pattern, but quickly generates turbulence and mixing of the fluids. Keep your eyes open, and you'll see
Keep your eyes
interesting
open.
flows like this all around you.
Okay. Okay, so very nice exposition of the Kelvin-Helmholtz instability. So we start from an undisturbed flow. There is a perturbation of the wave number k, and this creates this pattern, which are called billows. And then after that, as you see, we have mixing. Okay. So this can be also seen like this, for example, from another experiment. So this is a little bit different from the one that we saw on the video, because from the setup of the experiment, we are able to maintain the two fluid actually not mixed. Okay, so in the other situation, you have seen that the fluid were completely mixed. Okay, so the shear was enough to strongly mix completely. So the appearance of the Kelvin-Helmholtz was very short in time. Then everything was destroyed and completely mixed. In this case, the stratification is enough to destroy the billows, so the nice patterns of the Kelvin instability, but still keep the separation between the layer here and the layer here. Okay, so that's why we have this localized mixing, and delta H is also called mixing zone or mixed layer. So the turbulent mixing, which actually mixes this this layer here, is created by two mechanisms, dynamic mechanisms. One is the rolling, and the other one is the breaking. Okay, the rolling is the first one, which creates actually the billows, which practically overcome the potential barrier in a very localized point. And the second one is the breaking. So when the billows reach a situation which is unstable, and so there is a sort of mixing, of course, of the property of the fluid. Okay, so the explanation of the Kelvin-Helmholtz instability is mathematically very heavy. So what we just will give here is that from a theorem that you can find if you are curious over the book Kundu. Kundu is a beautiful book, and Kundu was also beautiful. I mean, beautiful, nice research. I mean, it's was exceptional researcher. And you can find it on in the library. I think there are even two copies. It's very nice. If you like GFD and environmental fluid dynamics, this is beautiful, really beautiful. And I think it should be chapter 12.6. So, I mean, this is not part of the course, huh? If you are curious. But what we want to know is that a sinusoidal perturbation of wave number L or K, whatever. So we have a sinusoidal perturbation, like we had in the plot before. So is unstable. So L means 2 pi over number. Okay. So the wave number is unstable when we have ρ2 square minus ρ1 square. So the square difference between the two layers multiplied by G, which is smaller than G, than multiplication of the two density, L, and then the velocity shear. So if this condition is satisfied, we have the instability. But this condition, what does it tell you? It tells you that L will be larger than a certain L minimum, which is equal to ρ2 square minus ρ1 square G over ρ1, ρ2, 1 minus U2 square. Okay? So when L will be larger than this value, than this minimum wave number, we have the instability. Which means that I will always have a short wave, that's why we short wave lambda, which is equal to 2 pi over the value of the minimum value of the wave number, which will be unstable, and from this short wave here, we will have that all the other waves, which will have wave number larger, which means wavelength shorter than this one, will be unstable. Okay? So that's why we say that a two-layer flow is always unstable for short waves. So if we use our Boussinesq approximation, so ρ2 over ρ1 similar to ρ0, we can substitute this only here, because here we have a multiplication, but we can write this like ρ2 minus ρ1 multiplied by ρ2 plus ρ1. So this remains ρ2 minus ρ1. This can be like, you can write, it's a sum, so we can write it like ρ2 multiplied by ρ1. So we have 2 over ρ0. This will be like ρ0 squared. So we can simplify ρ0 squared with that ρ0, and we remain with the density variation. So actually L min, the minimum wave number, will be equal to 2 ρ2 minus ρ1 G multiplied by ρ0 U1 U2 squared. So it's very similar to this term here. Okay? Actually, apart from the factor 2, is exactly the same. So, since we have said that delta H is order of lambda, because if the horizontal scale is lambda, okay, because it's the scale of the shorter wave, so this is the perturbation, and the length scale of the perturbation scales like 1 over L min, I can say that delta H will be order of lambda, will be over, lambda unstable, of 1 over L min, which means that will be order of ρ0 U1 minus U2 square over ρ2 ρ1 G. So delta H, if you like, put also the 2, no problem. Even if we take also the proportionality factor, the numerical factor between lambda, I will have a pi here, but it's not a problem. So, of course, our hypothesis was built on two semi-infinite planes. But if we come back to the initial situation, which is actually the most real situation, where actually we have H, which is not infinite, but is limited, we can say that when H is larger than delta H, it means that, So if h is smaller than delta, is larger than delta h, it means that h will be larger than this term here, which means that we will have, when h is larger than this one, it means that we will have h here, which will be larger than 1. Okay? So when h is larger than delta h, I will obtain this expression here. Okay? You just have to return up and down the situation. Okay? So just put this on the left-hand side, and you will have that this expression here is larger than 1. Okay? Which means, of course, that when h is larger than the mixing zone, I am in localized mixing. So I am actually mixing only on a layer which has a dimension delta h. In the other case, when h is smaller than delta h, actually we obtain the complete mixing, because in some sense the mixing zone, the mixing layer, is larger than the dimension of my system. Okay? And so I have the complete mixing. So we were able to find this distinction between complete mixing and localized mixing just by looking at a very simple flow, which is based on 2 layers, then in very complex flows, which actually are, considering a sort of instability analysis. I think there should be, yes, something more like very nice picture of the Kelvin-Helmholtz instability. So if you look Kelvin-Helmholtz instability, take a picture, because it's not very common to look at them. So both of the 2 pictures here were taken in Africa, Sahara Desert and Algeria, so over the Algerian sky, because you need very stable condition. Okay, you don't have to. You shouldn't have any kind of horizontal flow. You should have just like 2 flow, like stable, and one in one direction, the other one in the other. So an area of the sky, in this case, which is like stable horizontally, and what you have is just homogeneous flows in one direction and another one with a difference in density. Okay. Okay, see you tomorrow.
Yeah.
You should check that. I don't know why you're always sleeping. Bloody.
10 hours. That's why I slept for 6, 7.5. But still
Ti serve un passaggio in centrale?
No, direi no, perché devo fare un paio di domande per adesso prendo lo stesso tempo. Fammi un paio di domande.
Certo.
Nella scorsa lezione avevamo fatto, aveva spiegato questo. Perché? Cioè nel senso, qua abbiamo un'unghia con un'unghia
Più piccola.
breve, sì, perché vanno verso est, cioè abbiamo stop, invece che verso ovest, visto che noi abbiamo sempre che...
Allora, perché se tu guardi la funzione,
quello delle di gruppo,
Questo, la dispersion relationship, in questo caso tu hai velocità di fase e velocità di gruppo.
Esatto.
In quel caso stiamo parlando di velocità di gruppo, perché stiamo vedendo tutto il treno come si trasferisce l'energia. Allora la velocità di gruppo è la derivata. Allora se io vado in questa direzione qua, ovviamente è positiva. E quindi vuol dire, se è positiva, vuol dire che sto andando verso verso est. Questa vuol dire che è negativa e questo vuol dire. Allora vuol dire che quando è positiva io sto prendendo K piccoli.
Ah, ok.
Perché, scusami, K grandi. Perché se vado verso est, quindi questa è positiva, sono a grandi valori di K.
Ah, ok.
Grandi valori di K significano piccoli valori. Questo invece è il contrario. Nel nostro pianeta, di fatto, quello che si osserva è che quando vai verso nord le lunghezze d'onda si riducono.
Ok.
E quindi di conseguenza, ovvio, questa è una spiegazione molto, però ti dà l'idea di come i moti atmosferici tipicamente, se tu è come se anche, ecco, forse Giove dovrebbe funzionare in maniera un po' più chiara, perché Giove è fatto di fluido, di gas, e quindi quello che vedi è di fatto dovresti vedere che vicino all'equatore il moto è verso questa parte qua, verso ovest, e invece il polo là. E infatti in mezzo cosa succede? Si creano perché tu hai il mescolamento in orizzontale tra, diciamo, un fluido più freddo, perché ovviamente è riscaldato di meno dal sole, e un fluido più He's 18. You should talk with Riccardo, yes, because he's the...
Is it fine for you?
Well, I'm not here in any case. I won't be here because last year I was here and Riccardo was not in Italy. This case is the opposite. So yeah, for me, I will prepare the questions. I will give the question to Riccardo and then he will decide.
So let us ask.
Okay, we should ask.
Yeah, you have to ask him. Yes.
Because we have exam on 12 and
I can understand. I can understand. Sure, this is normal, but right.
Yeah.
Because I know that you have to finish before a certain date.
Yeah.
You cannot go start to the second term.
Poi noi avevamo detto che se io mi trovo sotto
Sì.
e quindi sono su z bassi,
Sì.
la temperatura cresce, giusto?
Allora, quando sono qui, nel caso di inversione termica, tu hai temperatura più fredda.
Ok, quindi contrario, cioè nel senso che sto dicendo è il contrario.
Sì, no, allora è giusto perché qui hai, se tu metti sulla stessa riga, in realtà anche qui non è così semplice la situazione.
Infatti,
però in realtà quello che tu hai è che in una situazione di forte stabilità, come puoi averla in questo caso,
ok,
tu per motivi che stanno in mezzo, cioè il fatto che tu hai il riscaldamento notturno, che praticamente di fatto tu cos'hai? Sul terreno tu hai riscaldamento giornaliero diurno e raffreddamento notturno. Praticamente il grosso se tu non avessi vento, non avessi turbolenza, e hai come nel deserto, tipicamente hai che sono 30 gradi di differenza, esattamente, o sugli altopiani, no? Quindi perché se non c'è vento, di fatto il sole riscalda la terra acquisisce calore, dopodiché quando va via cioè passiamo alla notte, la terra rilascia, a differenza del mare che invece lo trattiene. Allora, in questa cosa qua tu hai di fatto il modello più semplice è quello di avere riscaldamento diurno e raffreddamento notturno. Chiaramente se per motivi di avvezione o di termodinamici si crea la nebbia praticamente fa da tappo e quindi praticamente tu hai un continuo raffreddamento perché di fatto il sole non penetra e quindi praticamente hai degli strati che via via si formano uno sopra l'altro. C'è proprio un modello proprio molto ben fatto di queste poche parole che ti sto dicendo, però di fatto crei questo tappo che di fatto ti dà una temperatura una densità che è molto stratificata, quasi può diventare addirittura costante, quindi hai un sistema che è quasi omogeneo, però di fatto con temperatura che è fredda, cioè è molto più fredda, cosa che invece quindi puoi avere una situazione che hai di fatto la densità così, la temperatura così, dove in questo caso la diminuzione di temperatura non è dovuta al fatto che la densità è più alta, perché ovviamente Cioè, dovrebbe, e ci sono anche delle situazioni, dei fenomeni termodinamici dentro. Cosa succede? Che a questo punto tu hai temperatura fredda sotto e man mano che sali, praticamente finché lo strato di nebbia te lo consente, tu mantieni la temperatura, diciamo, o a quel livello lì, quindi se tu vai da qua a Opicina troverai più o meno, che ne so, 9 gradi, e quando sbuchi fuori, quindi hai uno sbalzo e la temperatura lì comincia, diciamo che è più calda di quella, ovviamente da quel punto in poi la temperatura comincia di nuovo a diminuire. Quindi tu potresti avere una cosa
sì, ho capito, cioè qua
più che altro
io, tipo fino a qua ho la...
Sì, puoi avere anche una cosa
okay.
che può essere tipo così, ok? Quindi tra così e così, ok? Quindi qui io ho temperatura che di fatto ho, se vuoi, anche così. Dipende molto, perché per esempio qua in regione questa cosa qui è chiarissima, ci sono dei casi in cui a Trieste in pianura hai, che ne so, 11 gradi, vai su a 2000 metri sono 13, 15, 20 gradi a volte, cioè sono inversioni termiche veramente molto forti. E con l'inversione
l'anno scorso, a dicembre.
Ed è una cosa tipica, noi non siamo una valle, però nelle valli di fatto è una cosa, valli alpine è una cosa che può capitare, in cui hai magari valli che non sono neanche vedono il sole per certi giorni, perché magari il sole non passa, e quindi lì se hai condizioni di stabilità è tutto bloccato, è tutto tappato.
Saluto.
Ciao.
Ah no, una era perché non posso... Perché quando faccio l'approssimazione di Boussinesq?
Sì.
Quando ho la gravità non posso...
Allora, questo forse perché ti hai riperso la lezione. Allora, Boussinesq
io
dice,
non ho fatto... Sì,
Boussinesq dice tu puoi